All right, so we are on to sorting 2, which is the second half of sorting. A couple people emailed me the following. I'll put this up here. I should have put it up before. This is actually, it's an XKCD comic on ineffective sorts. I'll put it up at the end again so you can see what's going on here. But we haven't talked about merge sort or quicksort, but half-hearted merge sort, where'd it go? There we go. Half-hearted merge sort says, if the list lets to return, you've got some pivot here, do it, and then I don't know what to do, and return. Right? So it's like, whatever. Quicksort, which we'll talk about a little later today. Basically, same thing. So there's this pivot thing, divide list in half. Is it sorted? Well, it doesn't matter yet. And then this is if you're doing a job interview, right? So let's see. The bigger one's going to list. When you're in an interview and you don't really know what you're talking about, like this becomes a big deal. And by the way, we will talk about quicksort today. We're going to spend a good bit of time talking about this quicksort algorithm. And I did a little poll of students, like grad students and other upperclassmen, and I asked them, have you ever gotten a quicksort question on an interview? And almost every one of their hands went up, right? So this is one of the ones you're definitely going to want to understand. If you can't actually code it, at least be able to explain what's going on. It's the first, as I think I said the other day, quicksort is the first real algorithm you see that is not like a trivial, oh, somebody could have figured this out, right? I mean, you certainly could have figured it out, but it's a very interesting way of doing sorting that we'll talk about, OK? And there's panic sort, and if it's sorted, returning. If it's sorted, this can't be happening. Basically, it keeps trying to check. And then it deletes the whole system under there. Kind of interesting. And then for those of you who know XKCD, you'll know if you hover over the thing, you get a little thing that tells you tells you a little extra joke. This one is stack sort. Connects to Stack Overflow, searches for sort a list, downloads it, and runs the code from there. Somebody actually wrote that so that it does that. So it will go to Stack Overflow, just search for it, and then start running various things and trying it out. Kind of cool. Yeah. So, all right. So here's what we're going to do today. First, a little quick Unix tip of the day on this program called sed, which is the stream editor. And I will talk about that. I'll show you what it can do. And then if you really dig into it, you'll go, wow, look what this can do. When I show it to you, you'll be like, whatever. But I promise you, if you look into it pretty deep, it's got a lot of interesting features about it, using these things called regular expressions, which we'll talk about. Then we'll do some sorts. We may, depending on time, we might not get to quite the last one. I rushed it a little earlier, so I'll try not to rush it into that one on this time. But we'll do 3 other big sorts that you definitely need to know. OK, questions before we get going? Homework 5 coming along OK? Going all right? The sorting. Remember, you can be creative on at least one of those ones, and you can do what you want. But should be kind of fun. OK, sed. There is a program on most Unix or Linux builds called sed, which stands for Stream Editor. And it actually started out as there's also a program called ed, which is just like a basic editor, but it's very much like one line at a time. You don't get much more than that. We're talking like 1960s when this was designed. Sed is a stream editor, meaning if you have a bunch of text and you stream that text through this program, the stream editor will actually change the text based on what you want it to change. OK, so it's kind of like a search and replace, but it's actually much more than that. The easiest way to use sed is to type sed and then s for search, I think, and then slash or some other character. Doesn't really matter as long as you use the same character each time. And then something you want to change to something you want it to be changed to, and then /g. And you just pipe in one file, and then you can pipe it out to another file. So let me show you an example of that. I have a file called green eggs and ham, which is as you might imagine, Dr. Seuss Green Eggs and Ham, right? It's a fun little poem, book, I guess. And I will not eat green eggs and ham. I do not like green eggs and ham. I do not like them, Sam, I am, et cetera, et cetera. Well, what if he didn't like blue eggs? Right? You know, he might not like blue eggs. So you can actually do the stream editor on to say change all instances of green to all instances of blue, and then pipe in green eggs and ham. And when it does that, it will actually change all of those instances. So let's see. Where'd it go here? There we go. I would not eat blue eggs and ham. I do not like them, Sam, I am, et cetera, et cetera. So it's a global search and replace that's pretty simple to use, right? And you say, OK, I can do that. Search and replace is not the hardest thing in the world. And that's all well and good. But what it's actually using here in this little search term, you can have lots of wildcards and other what we call regular expressions to change things in a million different ways. So you could have it so that it goes, if it was GRE and then uppercase E or lowercase e, and it would change that to BLU uppercase E or whatever. You can make it so that it changes things based on a search pattern and then does the whole search and replace. And again, while this doesn't seem like it's that big of a deal, this thing called regular expressions is this matching thing, which actually turns out to have lots and lots of use in various computer science disciplines. You will learn about regular expressions. We'll talk about them a little bit in a few weeks. Then you'll learn about regular expressions possibly in Comp 105, which is programming languages, and then definitely in Comp 170, which is theory of computation. They're like super duper powerful ways of figuring out if you have a certain pattern. And JavaScript uses lots of regular expressions. Perl uses expressions. Python uses regular expressions. All of your major languages have some way of using these regular expressions. So while it doesn't seem like that much doing, search and replace, it's actually kind of a really powerful thing. There are entire books and entire classes on how to do regular expressions properly. So you'll learn more about that later. There are lots and lots of options in SED as well. If we go and look at some of those, this is a whole tutorial on it, right? And there's a lot this was do a global search and replace, if you want to ignore case, if you want to use some file name to write to. Lots of different ways of doing this. And see how many options there are. So it just goes down and down and down and down and down, right? And so this thing's super duper powerful when it comes down to it. So this just keeps going, right? Lots and lots of stuff to learn how to do. Ranges of text and multiple commands and all sorts of stuff. So obviously, you don't have to know all those. But a quick Google search will get you what you need to know to use SED to do any kind of search and replace you want. OK? Questions on that? I didn't think there would be. We'll do regular expressions later and figure it out. OK, let's do a little more sorting. There's a sort we briefly mentioned the other day called merge sort. And just like its name, we will be merging lists that are actually already sorted. OK? And to do that, this is a divide and conquer algorithm. And what kind of asymptotic complexity are we thinking when we do divide and conquer? Logarithmic, right? And remember, for comparison sorts, in other words, where you're comparing two numbers together to swap them or not, the best you can do is n log n, which this will definitely give you, because the log n part comes from being able to divide it into parts. OK? Merge sort is almost always coded recursively. You don't have to, but it's easiest to do that way. And in general, you are merging some sorted lists together. OK? You're merging some sorted lists. And for instance, list 1, 3, 5, and 11, and list 2, 1, 8, and 10, become 1, 3, 5, 8, 10, and 11. OK? Here's what I want you to do. Take about 2 or 3 minutes. Talk to your neighbor if you want. Figure out if you can come up with an algorithm that will take list 1 and list 2, which are already sorted, going through them once, OK, and creating 1, 3, 5, 8, 10, and 11. OK? Try that on your own or with a partner for a couple minutes. This is a new array. You have a new array here. You're going to put these into. Okay, who thinks they know? I've started a little program up here, a little loop to do this. Okay, what do you think? How many people think they could probably do this if I said fill in the rest of this loop to do this? A couple people? Okay, good. You had your hand up first. What do you think?
Me?
Yeah, you can walk me through it, and then we'll write it if you want.
I guess you just compare the first indexes of each of the two L1 and L2.
Here are the first index, okay.
And then after, I can't have my glasses on, but I think that's a 1. So 1 is smaller.
It is 1. Yep, okay.
Put 1 in the
So you put 1 in here.
and you would prepend the index for L2 to the next one, and then you compare again.
So then L2 is going to change like this.
And then you also prepend the index.
And then you increment I, because that's what our loop is going to do, right? OK, so I actually kind of goofed here. This is not I equals 3. It's what? 6, yeah. OK, all right. So can we write this now?
Yeah.
What do you think? You said you could write it if you want.
My issue is that my only concern is that you don't want those L1, L2.
Oh, yeah, you're right. These should be outside. You're right. Let's move these outside. You're absolutely right. OK, so those are going to be outside. OK, good. Then what?
Once you do that, you would just continually check the two holders until you fill the holder.
OK, so if what?
So if L1 bracket L1
Lowercase l1, yeah.
is greater than L2 bracket L2,
L2 bracket L2, OK.
M of I
M of I.
gets it's greater than, so it gets L2.
OK, L2 of L2, OK. And what else?
And then you should iterate the int for L2.
So L2 plus plus, OK. And maybe an else, we're not going to run it. We're going to run a space. Else,
Can you also make that one or equal to? Just because one of them has to have the equal case in case for
OK, greater than or equal to, sure.
Doesn't mean equal.
Sorry? Oh, sorry, the wrong one. Here, there?
Yeah.
OK, greater than or equal to, OK. Yep, OK, got it.
And then you need an else if with the inverse.
OK, else is going to be the inverse, OK. OK, will this do it?
It will for this specific case, but it won't for all the time.
What would a case be where it'd be bad to do this?
What if
Yeah.
the array?
Hang on.
Do you
Go ahead.
want to repeat elements, like if 5 was in both lists?
You do want to repeat elements, yeah.
Okay.
Yeah. OK, what were you going to say, Alex?
What if the arrays, the lists you're merging aren't the same length?
OK, if the lists aren't the same length, that's one thing we have to deal with. What's another part? Yeah, Evan?
You go through one list but not the other.
Yeah, what if one list ends first? Right? How are we going to deal with that? Special case, yeah. There's probably not enough room here. But we should put the special case before this, right? OK, so maybe, or maybe we can say if L1, if L1 is greater than, I guess it would be greater than or equal to the size of L1, the big L1, that sort of thing.
Yeah.
Like basically so that you don't go, if you get to a point where you,
The last one forever.
yeah, and then what do you do with the other ones?
Just add it in.
Just add the rest of them. OK? So let's actually see this example. I've got it up here, so it's a little easier to see. 3, 5, and 11. So what you're going to do is you're going to go through both. You're going to start at the beginning of both, and then you're just going to check and compare the two. And whichever one is the smallest, that one gets put in the new array. And then you check again. So now 3 versus 8 will go in. And then 5 versus 8, the 5 is going to go in there. And then we're going to increment there. Now the 8 versus which one was it? 11? Yeah, 8 versus 11, the 8 goes in there. And then now the 10 versus 11 goes in there. And you do end up like exhausting one list. OK? Now L2 is actually, the index for L2 is bigger than L2. So we have to put the rest of L1 in the list. OK? So see how that works? And now they're merged. That's called like one little part of the merging. And if you have two lists, you just do that. What's the asymptotic complexity of that? N for whatever the total number is, right? The size of L1 plus size of L2. Yeah?
So normally you would have gone out of bounds on L2.
Yeah, exactly. Now we would have to have, like, you would have to make it so that you check both of them, right? If one is greater than, you just put the rest of the other ones in there. OK, we should probably clean that up a little bit. That's the idea. OK, you're going to basically do that. OK, so everybody kind of gets the idea of how we're going to do a merge if we have two lists that are separate. Now, how do we get two lists that are already sorted? Because that's the point, right? We've got to have two lists to sort. Then how do we get lists that are already sorted? If we have, let's just say we have, let's go back to the, yeah, let's see. That one's already sorted. So let's say we had, let's say this was one big array, 3, 5, 11, 1, 8, 10. OK? How do you get to a point where there's individual, or there's lists that are actually already sorted? What do you think?
Make them lists of size 1.
Make them lists of size 1. Yeah, once you have lists of size 1, what? It's already sorted, right? So if you break it down, and you can do that recursively, just divide it in half, 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 you can actually get them so there are lists of 1. And then you've, by default, got sorted lists. Two sorted lists of 1 can get merged using this and do the same thing, and it's all recursive. So watch how it actually happens. OK? The algorithm itself is divide the unsorted lists into n sublists, each containing one element, exactly as Amanda said. And then you repeatedly merge the sublists to produce new sorted sublists until there's only one sublist remaining. OK? And that's now going to be a sorted list. OK? So you recursively do that. Now here's how it actually works. Here's our example. So we start out with the numbers on the top, and we break them in half. Now it's not obviously exactly half in this case, because this was an odd number of items. OK, but that won't actually matter. It's kind of a special case, but it really won't matter in the big picture. Divide it in 2. Divide each of those lists in 2. Divide each of those lists in 2. And then finally divide this one in 2. OK? That's actually a logarithmic number of steps, right? And doesn't it look almost like a little tree? Like it's kind of going out like that? It's kind of that way. But now that you've got all these individual ones, you can start merging things together. OK? So the first thing you do is you merge these two. All right? And that will create a 0 and a 4. And then you have to do it. You have to merge these ones and this one. And then this one and 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 this one. That's how they actually get merged together. OK? So you're going to merge 86 and 0 and 4. So it should become 0, 4, 86. That's going to be your next merge. And then same thing with the other ones. OK? Well, guess what? Now you've got a merged list like this. And you have, and now you're going to merge this one and this one. And this one and this one up one more level, like that. And now notice both of these are now individually sorted, because you just merged them and made them sorted. OK, and then you have one more merge for the other ones. And you run through the same algorithm again. And you merge them all together. Almost all of them change position in some form. And then there you go. OK, another traversal back up logarithmically, but that's it. Yeah? Nathan?
Is this memory intensive?
Ah, that's a good question. It is a bit memory intensive. You can get it so that you only have to create basically one copy, because the individual other copies don't. If you do it in kind of a naive way, you do have to create like a copy, then another copy of all the ones, then another. And you do have a lot of different like smaller arrays. So it is memory intensive. It's not in place. Okay, this is not by default an in-place algorithm. Okay, and it's actually very easy not to do in place. Like this is pretty simple. You got a question?
It is possible to do this in place, though, right?
Sure, it's possible to do it in place. And in fact, if you want, for your homework assignment, you can certainly try to do it in place. The problem with in place is, and this is on another slide, there's going to be lots of swapping back and forth, right? Because you're going to have to, let's say you're going to be moving like this one to place 1. Well, while this one goes to place 1, this one's got to be out of place. So then you got to deal with 6, but you don't know where 6 is going to go yet because you're walking through it. So it's a little trickier. It would be kind of fun to do, but you may not be you might end up with a very high constant in your asymptotic behavior because of that. So it's generally not done in place. You could, but it's not generally not done that way. You had a question, Tafar? OK. Anybody else? Somebody else had their hand up? No? OK, but you see how this is done recursively. Now here's the some more details about it. Yeah, we already talked about that. Can be completed in place. It uses double storage. Now this is if you do it correctly, where you don't create a new array and another new array, new array. You can actually do it so that you only use twice as much memory. It's easy to do it without like going through that. But it's fast. You don't need to shift any elements. Remember, insertion sort had lots of shifting back and forth. None of that's necessary. And it does take double the memory. So you're not going to want to do a memory intensive. Like if you do this on an Arduino or something, you might run out of memory. Okay, the odds are slim that you would run out of memory for our tests. I'm not going to give you tests where you've got so much memory that you can't put it into an array or a couple different, or multiple arrays. Okay. All right. Questions on this? That's merge sort. It is a very good one. It's logarithmic behavior. Okay. It does. The best case is, or the worst case, n log n. That's great. Best case, n log n. Average case, n log n. A very good sort. Another benefit to this sort is it is stable. In other words, no elements are going to fly over, like cross over each other if you're doing this. No elements will actually like be out of place if they started in a particular order. So that's nice. Okay. Some of the other ones we're going to do are not that way. Okay. That's merge sort. Pretty standard one. I can see getting asked that on an interview question too. What's that? OK. All right. On to the big one. So Quicksort. It's not called Quicksort for nothing. All right. It's actually a really fast sort in general. OK. And it's often faster than most other sorts. OK. Another n log n, but with a lower time like a lower constant. It's like better than most other ones. Problem is, worst case, n squared. Okay, and that's not good. And we will see why that. I'm going to leave that one hidden for a little bit, why this case, but somebody will figure it out. You guys will probably figure it out pretty quickly when it becomes n squared. Okay, that rarely occurs, but it occurs in some very important times. So we have to be careful about that. Okay. Going to be Quicksort. So this is kind of the setup. It's a fast sort that's unique in the way it does its thing, but it's got some issues that you have to deal with at some point or another, like the n squared behavior. You want to avoid that if you can. Turns out it's pretty easy to avoid it. Okay. All right. It is indeed another divide and conquer. That's going to give you this logarithmic behavior. Okay. And here's how it works. Take a list and divide it into two lists. OK, that's not weird. But the two lists have the following properties. The low elements and the high elements are going to be in the different lists, depending on what we call a pivot. OK, so you're going to have two lists, and there's going to be one number that's going to say all the numbers that are less than that go on one side. All the numbers that are greater go on the other side. OK, that's how it's going to work. And then you recursively call the algorithm again to do the exact same thing. OK, this is called the pivot, which I believe is on the next thing here. Here's the actual algorithm. And as I said, this is really the first big algorithm that we talk about. And it's not that bad, but it's kind of unique. Pick an element. Here's the algorithm. Pick an element, call it the pivot. OK? Reorder the list so that the items below that pivot are on one side, generally the left. The items that are higher than that pivot are on the right. Ties, you get to decide. Ties can go on one side or the other. Okay? That's called the partitioning. Okay? And once you're done with that, you've got low numbers, some pivot, and then high numbers. That pivot happens to be in the perfect position at the end. Does that make sense? Why? Because everything else is lower than it, and everything else is bigger than it on the other side. So it has to be in the right place. That's the first thing. Yeah?
If you use the pivot at like a middle point, what happens if you have not the middle value here?
Yeah, if you don't have the middle value, you just end up with a shorter sublist and a longer sublist.
I'll use the expand your array.
Nope, your array is not going to change. Your array size is not going to change. You're going to be doing. We're actually going to do it in place in the end. You can do it two different ways. I'll show you both, but you'll see. So keep that idea in the back of your mind, like what's going on if you pick one that's not in the middle of the numbers, okay? Because that becomes important, okay? And then you recursively apply this to the sublist that you've now created. And if you do that again, partition each sublist, pick a pivot, make the lower and higher of that, eventually you will end up with a bunch of lists that are all in order, okay? The base case is if you have a list of 0 elements or 1 element, because they're already sorted. If it's a 0 element, obviously it's sorted. If it's 1 element, obviously it's sorted as well. Okay? So start thinking of this. Yeah?
Could you do this in place?
You can do it in place. I'll show you how to do that. The in-place algorithm is cool. You'll have to see it a couple times before you get how it works, but I'll show it to you. Okay? All right. So we have two different types of algorithms. The naive one is the non-in-place one. We call it naive. I don't know why. It's still interesting enough. But this one, you just create new lists. So you can actually, it's easier to kind of understand when you create two lists. Okay? And then you end up with an overhead of more memory, kind of like with merge sort. Same idea. We can also perform it in place. I'll show you that one too. And this is the one that you should know, the in-place one. At least be able to describe more or less how it happens. Okay? All right, let's go through the naive algorithm first, the one where we create more lists. Here's your pivot. Right now, we're just going to pick the leftmost element as your pivot, straight off the bat. We'll talk about why that might not be a good idea later. But let's pick the leftmost element. Okay? If it's a 6, now we're going to have the two sublists, and we're going to go through the rest of the list. And for every number that's less than 6, it's going to go on that side. And for every number that's greater than 6, it's going to go on the other side. And 6 is going to be in the middle. That make sense? How that works? We've got a less than 6 array and a greater than 6 array. And it doesn't matter. The order of those subarrays we'll deal with later. But for now, you've just got that. And then 6 is going to go right in the middle. And then you're going to do the same thing for the two sublists you created. You don't have to worry about 6. Turns out the algorithm I show you for in place, I show you it with the 6 as one of them, but it doesn't actually matter. Remember, that's already in the right place. It's not going to change no matter what. Okay? So now you're going to pick the pivot of 5 and the pivot of 9, because the 5 is the leftmost element of this array, and the 9 is the leftmost element of this array. In this case, well, there are no numbers here that are greater than 5, and everybody else is less than 5. So you end up over here, those ones, and then nothing ends up greater than 5. The exact opposite is true here. Nothing is less than 9, and the only other one left is greater than 12. You have to call a recursive call for each of these. What's interesting about that is, remember the video I showed you, where there was the standard sort from the library, and it was those jagged edges? And I said, at the end, I said, hey, for those jagged edges, you use an insertion sort. This is the case where you might use an insertion sort, when you've got a very small rest of your array in Quicksort. In fact, if you want to make your Quicksort really fast, make an insertion sort for when you get down to like 10 elements. It'll be really fast. Okay? But we'll talk more about that. So now you've got 3 and 4. You still have to partition the 3 and 4 one, because it's 2 elements. Okay, the rest, watch, look, they're already in order. Right? 5, 6, 9, and 12. 3 and 4, you're going to pick a pivot of 3. So there will be nothing. There will actually be, let's see, did I do this wrong? I think I should have. The pivot, I think I picked the wrong pivot on that one. But it ends up with 3, 4, 5, 6, 9, and 12. And now you've got your arrays, and you can put them back together, and you've got a sorted array. Okay? That's how Quicksort works. Pick a pivot, left and right, do it again. That's it. The insertion sort would make sense when you have like 10 or 15 elements. A small amount, but because remember, each one of these recursive calls takes up more time. And so if you're just doing an insertion sort, you're going to gain a little bit of benefit on that. So, all right. That's the naive one. We call it the naive one. That's the one where you create more and more one. Now let's talk about the in place one. Okay? Here's the in place idea. Oops, yeah. Sorry. Oh, sorry. Go ahead. Thanks.
How do you, for the naive sort, how do you figure out how many elements are in the array that you have to make? Do you like save a number and then?
Yeah. If you notice for the homework assignment, I did that by giving you a little struct that's called array with length. Right? So you have to, in C and C++, unfortunately, arrays don't have a defined length. Like you can, they end when they end, right? So you have to keep that separately. So that's how you do it in this. Other languages, you can actually call the length easy enough, right? So just because we're using C++. If you were using Java, you could easily figure that out. OK. All right. Ready for this? Pick a pivot. Once you've picked a pivot, set 2 more pointers, or I guess they're indexes, not pointers. One being to the first element, one being to the last element. Call it left and call it right. That part makes sense. Any idea which direction left moves? To the right. And then right moves to the left. But they're called left and right because that's where they are on the picture. What you're going to do, and this is important, do this step first. A lot of people try to do the left one first, and then it screws it up. There is a way to do the left one first. You just have to rethink it. I'm going to show you this algorithm. And if you're going to build this, I would suggest doing it exactly like this and then trying to make it better. Because there are some ways to make it a little bit better. But OK, we've picked our pivot. And you might say, well, wait a minute. Why am I putting left there? Why can't I put left there? You can put left there. Just be careful about it. Because there are some caveats here. OK? You're going to try to be tricky when you do this. And then you're going to debug it for 17 hours. Because you're going to go, what's going on? Make it work first with exactly this algorithm. You're going to say, no, it's wasting time. And do it first. You'll see. So left is over here. Right is over here. Here's the deal. We are going to take right, and we're going to look at its value. And we're going to say, should that be to the left of the pivot? In this case, yes, because 4 is less than 6. OK? If it's not, we're going to keep moving the right to the left until we get to one that is supposed to be to the left of the pivot. Right now, it happens to be already there. Once you've got right on a value that's supposed to be to the left of the pivot, you do the left going the other way until it hits a value that's supposed to be to the right of the pivot. So we're going to take left, and we're going to say 6 does not need to be to the right of 6. 5 does not need to be to the right of 6. 9 needs to be to the right of 6. OK? So you're going to do that. You're going to keep moving that over there. And well, I guess I gave it away. But since you've got one that's supposed to be to the left and one that's supposed to be to the right, swap those values. OK? Because that makes the most sense. Because look, 9 should be somewhere over here, and 4 should be somewhere over there. So you might as well swap them. OK? Just do a quick little swap. This is why it's in place, and this is why it's kind of clever. OK. Now, what's the next thing you think you might do? Do it again. Should we say, look, we just swapped these. Let's move right to here and left to here? No. You'd think you'd do that. And you might be able to want to be clever about that. Just don't quite yet. OK? You'll see why in a minute. OK, start with the right one. See if it should be to the left of the pivot. OK? Oh, sorry, we haven't swapped it yet. Now we swap it. There we go. OK? See if this one needs to be, even though we just swapped it, and we know it doesn't need to be left of the pivot, just check it. OK? If it's to the left, if it should be to the left, which it shouldn't, then stop. If it shouldn't be to the left, go to the next one. We're going to hit 3. That should be to the left. And then we're going to go and check 4 to find where it should be to the right. Nope, 4 should not be to the right of 6. 12 should be to the right of 6. And then you're going to, swap them. OK? You keep doing this until the left and the right are the same value. So the next thing you do, did we swap these yet? No. Swap them. When we swap them, the right, now we check right. Does it need to be to the left of the pivot? No. Move here, and guess what? They cross. OK? When they're the same, then what do you actually think you do? I'm not going to go ahead so you can think about it. So now they're going to be the same. What's the one last thing that has to happen? You swap this one with the pivot, and guess what? It'll be 3, 5, 4, 6, 12, 9. When they cross, that's where you've gotten to the point where no more, like nothing, that's where the pivot needs to go. OK? And so you swap the pivot and the one that you just crossed, like that. OK? So that's how it works. All right? And you've now got a partitioned piece. Anybody want to see that again? No, nobody? I'm showing it to you again. We won't have to go fast through it. We won't go slow through it. OK? Start with a pivot. Put your left and your right. Make the right go to the left until it has a value that should be to the left of the pivot. It's already there, as it turns out. You do one check, and you say, oh, I don't need to move the right anywhere. Then you go and move the left until it gets to a value that should be to the right of the pivot. OK? Swap those two. Boop. OK? And then start over again. Should 9 be to the left of the pivot? No. Should 3 be to the left of the pivot? Yes. Go to the other one. Should 4 be to the right of the pivot? No. Goes to 12. All right. Should 12 be to the right of the pivot? Yes, it should. Swap them. OK? And then start over again. Should the right, or should 3 be to the left of the pivot? No. Oh, I didn't swap them. Should 12 be to the left of the pivot? Then no. So move that one over there, and it crosses. When it crosses, swap with the pivot. OK, that's how it works. And now you've got a sorted list on the, or a smaller list on the left, bigger list on the right. OK. All right, now what do we have to do? The same for the first half and same for the second half. Now, the easy way to do it is to do this. Well, you're going to recursively call Quicksort on the two new partitions. Remember, I've drawn it this way, but remember, we're still dealing with one array here. OK? I put it like this. I'm saying Quicksort from 0 to 3. You'd think, hey, wait a minute, the 6 is already in the place it needs to be, so why are we including it? It turns out that the reason it's easy to do that is because the reason it kind of makes sense to do that is because sometimes if you don't do that, you can end up trying to call Quicksort on like 0, -1, or something weird like that. So you just have to be a little careful on that. OK, what's that? Yeah, if it ends up being the first one, you'd end up like having a. So you can do it this way. 6 will not move when you do this, because even no matter what pivot you pick, you'll still just jump one over. So it's one more operation, but it tends to simplify things a little bit. If you want to be sneaky and just call Quicksort array 0, 2, that's fine as well. It will work, I believe, for all cases, but you just have to be a little careful with it. So we're going to Quicksort that one. Same thing. Let's pick the pivot as 3, the left one. OK? And you're going to pick the pivot as 3. Well, as it turns out, picking a pivot of 3, everything is to the right of 3. Right? So what would happen here is the right one, 6 should not be to the left of 3. 4 should not be to the left of 3. 5 should not be to the left of 3. They just crossed. What do you do when they cross? Swap the pivot. So you're going to swap 3 with 3. You could say, oh, I'll just skip that. I'll make it write an if statement, and I'll check it, and then I'll swap it only if it's different. You're probably going to take just as much time doing that if check as you are doing the swap. Right? So in some sense, sometimes it makes sense to, like, you might think, well, this is dumb. I'm swapping 3 with 3. Well, in real life, it's probably just as quick to swap 3 with 3 as to check if the indexes are the same. Right? You might gain a little bit. And you can tweak this. If you're building your own, you can definitely tweak it. As I said before, make sure it's right before you try tweaking it. Okay? Start with a working algorithm before you say, oh, I'll make this change. Okay? And then they cross, so we swap it, and that's it. And then we're going to do the same thing for the 12 and the 9, and the same thing for 3 and the 5, 4, 6. 3 is the base case, right? Because it's only an element of 1. You just return. You don't need to worry about returning the index or whatever. You can enter -1 for the index or whatever, just so that you know that it's just a you don't have to do anything. Okay, and then we're performing quicksort on the other one and performing quicksort on 9, and in the end it will become 3, 4, 5, 6, 7, 8, or 3, 4, 5, 6, 9, 12. Okay. Questions on the in-place algorithm for quicksort? No? OK, good. This one, again, is a little bit tricky. Now, choosing the pivot. Did anybody, we had a little concern earlier about choosing the pivot. Anybody think it might be a bad idea to choose the leftmost pivot?
Yes.
Why? What do you think?
Because then if you can run into the same problem that we just did, you can have your pointers running all the way through the array at the same time.
Yeah, you can have one running through the array every single time. What order would it be in such that picking the left as the pivot would always be bad? Sorted. 1, 9, 20, 50, 57, and 98. If we pick a pivot of 1, guess what? 1 ends up by itself, and then all the rest end up on the right. And then you go ahead and do the partition on this one, and 9 ends up by itself, right? And then you do this one, and 20 ends up by itself. Guess what kind of behavior we now have? N² behavior. And that's how you get it. So it turns out that the default way of doing quicksort for a sorted list turns out to be the worst way of doing it. OK? And many times, you will sort either nearly sorted lists or already sorted lists because it comes to you in a sorted fashion. Right? So you don't want to make your supposedly quick sort be not quick by picking the wrong pivot. OK, well, we've got some other choices. What other choices do we have? We've got a random pivot. If we choose a random pivot, that's probably the best idea, right? Because that's some in the middle. No matter how your data is organized, the pivot's going to be, on average, not the least one, right? It's going to be somewhere kind of in the middle on average. What do you guys know about random numbers? This is an interesting topic, random numbers. Yeah?
Aren't they actually in a computer not random? Like they're based off of a function like on how long it's been since 19 something.
Totally depends. But yeah, your point about numbers in a computer that are, quote, random are generally not random. So when you take dice and you throw them, right, you're going to get a random number, unless somebody's loaded the dice so they always come up and you're a gambler or something, right? But you're going to roll dice, and they're going to come up somewhat, they're going to be a random number, right? And that's because the forces of nature have kind of deemed that there's quantum mechanical effects and all sorts of stuff where things like bouncing dice are going to be a random order, right? As long as it's not weighted. In a computer, you can't mathematically come up with a random number. Let that sink in for a second. There is no way to mathematically generate a random number. Okay, we can mathematically generate what we call pseudo-random numbers, which look random, but can be repeated. Right? You can actually go and you can rerun the algorithm, and you'll get the same order again. Right? That's not random. Okay? So we have to worry about that. Now, it turns out that some computers, like computers running Linux, actually build in real-life randomness into their computers, into the system, where they actually take how many times the hard drive has been spinning, or how much your mouse has moved out left and right, or how many keys you've struck in the last 10 minutes or whatever. Those are kind of random events, and there's lots of formulas to make those random. So that's actually real randomness. It's generally not the way we do these things. For this, we could care less if it's a real random. We just want it to look random. So you can come up with a pretty easy function that's fast to pick a random number. So that's one way to do it. Feel free to do that for your homework assignment. Another way to do it, what's some other ones we could pick instead of the random one? The first one we already did, and that's not so good. Middle number. What do you mean by middle number?
Just like in the array, whatever the middle index.
Like whatever the middle index is. OK, so that's a little different than the middle of the numbers themselves, right? So yeah, you could pick the one in the middle. Good, that's a pretty good choice. Because generally, your data won't come to you such that the middle here is the least, and then the middles here are the least, and then the middles here are the least. That's like a weird, odd ordering, right? Whereas sort is not. Yeah? Katie.
do some like pre-operations at the beginning to guarantee you can hit it?
To guarantee what?
To guarantee you can hit it.
How do you do that?
You divide all the data into groups of five elements,
OK, divide the data into groups. OK.
and then you brute force sort those 5 elements.
Yeah.
Into sets of 5 elements, and then you find the median of each one, and then you find the median of the median.
OK. I think is this something you talked about in the other class? Yeah. That's not bad, but it's adding to your poor behavior. Like doing all that, it might make a difference, like to get a good median, but it might take too long. Like it might not be the best idea to do something like that. So you can do something. There are various ways of doing that. I like the idea of picking the index in the middle, because generally that's going to be a really easy one to do, and it's also going to be fast, and you're not going to have to like do any other calculations. 2 things about that. First thing, if you know the left index and the right index, how do you find the one in the middle? How do you find an average of 2 numbers? Add them and divide by 2. There's a problem with that. And this goes into a little more detail. I'm going to take the time on this because some of you might find it interesting. If you tried to do that, if you tried to say the left index plus the right index divided by 2, you can end up in a situation where your computer will overflow those numbers, and you'll end up getting bogus data out of it. Like you'll get a bogus middle. OK? Here's why. When you say int a, that a can be represented in memory somewhere. And normally, the way it is these days, normally that's a 32-bit integer. You've probably heard that your computers now are all 64-bit and so forth, right? Integers are generally still 32-bit. You could do a long, which is generally going to be 64-bit. But 32 bits means that you can represent 2 to the 32 different numbers, OK, which is a pretty big amount. Anybody know what 2 to the 32 is roughly? How big it is? Close. Not 6 billion. 4 billion. OK, it's about 4 billion different numbers. But let's say we do int. Are ints signed or unsigned? In other words, can you have negative integers for ints? You can say -3. A is -3, right? So that splits the total in what? Basically, the total positive ones in half. So you basically can get up to 2 billion positive numbers. All right, you ready for this? That means that 2 billion is the biggest number you can represent using an integer, roughly 2 billion. OK, what if we had our array and it was about, I don't know, 2 billion, or let's say 1 billion elements long. OK, let's make it a little bit better than that. Let's make it 1.5 billion elements long. So you want to sort a 1.5 billion element list. Well, when you get to the end, you might have index here being 1.6 billion, or 1.2 billion rather, and this one being 1.3 billion. What happens when you add 1.2 billion to 1.3 billion? You get 2.5 billion, and that's bigger than the number that you can represent. And the computer says, here's some garbage for you. Right? It says you can't represent that number. So what you can do instead, and it says this is just a little trick. And computer scientists are full of these little tricks. OK, it's a little trick. Instead of saying left plus right divided by 2, you can change that, and you can say left plus right minus left divided by 2. Mathematically, aren't these two the same? Let's figure it out. This one becomes left plus right over 2 minus left over 2. What's left minus left over 2? Left over 2 plus right over 2. And then common denominator becomes left plus right over 2. Those two things are equal to each other. So this actually is a correct representation. But guess what? A big number minus another number, if it's to the right of it or to the left of it, is going to be less than this overflow number. You can't subtract 2 numbers when one's smaller and get a bigger number, right? It's impossible. And then you can add the other one on there, and you will get the middle value. Okay, just a little kind of extra little thing on why you should use this to figure out your middle number versus the other one. Okay? Now, if you pick your middle value to be your pivot, I don't have it up here. If you pick your middle value to be your pivot, let's say it turned out like this before. You pick that. What's the problem there? Any ideas? Does our algorithm break? Yeah. At some point, your left and right might get there, and then you'd have to do some swapping. But yeah, I mean, sometimes your right might have to cross over this and then be there, and then eventually you might have to swap. But the nice thing about doing the algorithm we had before was that we were always putting something that had to be to the left of the pivot it's putting it into the first value, right? Because the pivot was always the first value. See how that was important? Okay, it turns out it was important. There are ways around this. The easiest thing to do, I'll tell you right now, the easiest thing to do, what do you think?
I was just trying to figure it out, like take the pivot out, put the one that's supposed to be on the right of the pivot where the pivot was.
Yeah. Just swap the pivot and the first value and make it the first one, right? Pick the one in the middle and then say swap it real quick, because that's pretty fast to do, and then make it the one on the left, and then run the algorithm just like normal. Okay? If you want to avoid that, to make it like super fast, you could figure out what has to happen in the various corner cases here. And by all means, do that for your homework assignment. But first, do it so that it swaps it and then does it. See what I mean? Same idea here. Start with a working program, tweak it a little bit, make sure it's still working, tweak it a little bit, make sure it's still working, tweak it a little bit, right? If you end up not being able to go any farther than the regular algorithm here, perfect. I'm perfectly happy with that, right? It will still be fast. It just won't be, it might not be quite as fast as it absolutely could be. Okay? So there's some ideas. Yeah?
I'm just confused. If you're going to take the middle one and then put it on the left, why didn't you just take the left one to begin with?
Remember, what if this was already sorted? By picking the left one, the idea is that if you pick the left one, it could end up, it's the smallest if it's an already sorted list. Pick the one in the middle, it's not the smallest, right? And if it was a sorted list, you'd have a great pivot, right? Because you picked the one literally in the middle of the list, right? Yeah. Okay. And sorting an already sorted list actually does take some time in Quicksort, because you're still taking the same amount of time, right? More or less. Okay, so that's Quicksort for the most part. A couple other interesting things about it. Repeated elements in Quicksort do not cause for a nice Quicksort, right? Think about what happens with repeated elements. Let's go back to the what? Yeah, in the animation, that was actually slower. Let's go to let's see, sorting. I think it's sorting. There we go. Sortingalgorithms.com. There you go. All right. OK, so let's look at Quicksort here. If we look at Quicksort and we actually run them all, the random one, the nearly sorted, they go. This is actually kind of slower than I thought, but they all go pretty fast over there. And you can kind of see now a little bit what's going on. But take a look at all the random, nearly sorted, and reversed are all good. And the few unique, still going, still going, still going, right? Why is that the case? What happens if you have a bunch of numbers that are nearly the same? I mean, let's just take the absolute worst case. What's your favorite digit? Alexandria, what's your favorite digit? 5. 5, 5, 5, 5, 5. If we're going to sort that with Quicksort, pick a pivot. Be fancy about it. Pick a random one.
5.
All right, 5. It's this. Let's pick this one, right? Well, you swap it with this one. OK, so this is now the pivot. OK, should 5 go to the left of the pivot? No. Did 5 go to the left of the pivot? No. Da 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 da. Swap 5 with 5. Now we're going to Quicksort 5 and all these ones. Pick a good pivot. You can't pick a good pivot. There is no good pivot, right? So Quicksort completely breaks down when even if you pick the perfect random pivot, completely breaks down with a list where everything's the same. Okay? So we have to do something else about that. All right? That's where we end up with this one called Quick3. Okay, remember we had a Quick3? The Quick3 says, look, if your pivot happens to be duplicated, create a third array, or a third place for that. Okay, instead of having just 2 sides, Now you've got two sides plus a middle one. And then whenever you're done with that middle, like if you pick a pivot and it's got lots in the middle, ignore all that middle one. Boom. And then you've got the two other ones. And what if they have duplicates? Well, you're going to ignore a good portion of it after you quicksort that. Well, watch how fast this one is. Few unique, right? See how fast it boom, you know? It actually beats all of them, right? Because you really only have to sort 4 different things now, right? That middle box that you've now created is going to get big chunks every time you pick a pivot. So it ends up being really fast. So most implementations of Quicksort in the real world will account for this. And I guarantee you when we test your code, by the way, I should talk to you about testing the code for this assignment. You have to test your own code, like for the most part, right? I mean, we do a little test to make sure that it's actually doing more or less what we want it to do. But for this test, we will test 0 elements. We're going to say, sort these 0 elements. You would be surprised at how many people's code crashes trying to sort 0 elements, because they didn't think about it, right? Now you guys won't, which is good. We'll ask you to sort 1 element. We'll ask you to sort 2 elements. We'll ask you to sort 10. We'll ask you to sort 11 or whatever, some odd number, right? And then we'll ask you to sort like 100,000 and a million. Well, probably not a million, up to 100,000. You should be able to sort up to 100,000 in like less than a minute for all your algorithms. Less than 2 minutes maybe for all your algorithms. Okay? But we're going to test that. And we're also going to test random. We're going to test nearly sorted. We're going to test reversed. We're going to test a few unique values. We're going to do all these tests on your things. And then, this is actually kind of one of the neat things about this assignment. We're going to give you the data. And this is going to be an in-person grading session. So you're actually going to have to set up a time with 2 TAs. And it'll be all set up basically by your lab TAs. Will kind of do the initial setup. And you're going to go and find 20 minutes of time after the assignment's done where you sit down with these TAs. And then you look at your results. And the TAs will ask you questions about all your sorts. Say, why did you do this? And why did you do this? And where's your comments? And what's the asymptotic complexity of this sort? And why does this data show it? Because we will give you lots and lots of data. So it's actually kind of a fun assignment to get graded, because you get it graded for real in real life. Grade on that's when you get the grade, yeah. Well, they might not give it to you right then, but they will. Yeah, you grade it on what you say in that session and what your code is and what it looks like and all that. This is not a stressful thing. It should be. It's a good learning experience, actually. Yeah. Okay. But you'll actually do it. So bottom line, make sure that you are like doing these tests yourself, and make sure you understand all the sorts you wrote, right? Because you can absolutely tell when somebody just copied the algorithm straight up. Because you're like, what's the asymptotic complexity? I don't know. You know? You go, no, wrong answer. So make sure you're doing that. OK. Let's move on. That was Quicksort. Quicksort, sort 3 groups, right? So repeated elements, n squared, make it into 3 groups. Yeah.
Is there a way to randomly generate a lot of the data to test?
We've given you a bunch of test data.
Right.
So if you look at that, those are the easiest ones. And then it's pretty easy to do. I've actually got a little program, a Python script that I can send you guys. I can put it on Piazza if you want to generate more data. Sure. Yeah, pretty easy. Or you can just generate it with, you know, a little loop and couts and whatever, and capture that. It's pretty easy to do. Yeah. Yeah. I don't expect you to. No, Quicksort is fine. You do not have to do Quick 3. If you want to do it, it's one of your sorts. That's awesome. Yeah. OK. Good. Anybody else? Yeah.
This might have already been covered, like for the Unix Tip or something. But is there a way to very quickly compare like 2 blocks of text, like
diff?
Okay.
Yeah. If you use diff on 2 files, that'll do it. Yeah. The diff command. Yeah. I can. I thought we did a little Unix tip of the day on that, but maybe not. I don't remember. OK. All right. So that's Quicksort. OK. Another sort. And the complexity, best time, worst case, n squared. But most of the time, you can avoid that if you do things smartly. Average, n log n. Space complexity. You do have extra with both cases because they count the fact that you have to do this recursively. So you've got an extra kind of like the overhead of doing these recursive calls gives you extra space. But in the end, it's still a pretty good, like overall, really good algorithm. OK. All right. The next one we're going to talk about is this sort called radix sort. I like talking about this sort because it's so unique. And it's different than all the other sorts. It is not a comparison sort. At no time during the running of this algorithm will two numbers be compared against each other. Okay? Yet you will end up with a sorted list, which is cool. What radix sort does is it uses these things called buckets. Okay? And the buckets are based on the digits in this for decimal numbers 0 through 9. So you're going to have 10 buckets. One bucket's going to be the 0 bucket. The next bucket's going to be the 1 bucket, 2, 3, up to 9. Okay? And those buckets are going to be filled based on the decimal place that you're currently working on. Okay? If we have a number 542, okay, there's 3 digits there. You can look at the tens digit, the hundreds digit, or the thousand. Did I do that wrong? The ones digit, the tens digit, or the hundreds digit. I need to go back to 2nd grade. All right, the ones digit, the tens digit, or the hundreds digit. And depending on what that digit is, that will tell you what bucket things go into. Okay? Which is the most significant digit here? Which one means the most to this number? It's not the 4, because that's in the middle, right? But is it the 5 or the 2? Why is the 5 more important? Because 500 is bigger than 2. Not a bad answer. This leads me into my favorite joke. All right? I love this joke. 2 guys walk into a natural history museum, like the Museum of Science. And as they're walking down, they see this giant skeleton of a Tyrannosaurus Rex. Right? And the one guy turns to his friend and he says, "See that T-Rex over there? That T-Rex is 1,000,004 years old." And the other guy goes, "How do you know it's 1,000,004 years old?" And he says, "Well, I was here 4 years ago and they told me it was 1,000,000 years old." Right? It's because it's significant digits, right? That 4 at the end does not matter. That dinosaur will be 1,000,000 years old for another 500,000 years. Right? Because those digits don't actually matter to any of that. Yeah?
Isn't this just like putting all the array into a prefix tree for numbers?
A prefix tree for numbers? No, not quite. Not quite. You'll see how it works. You'll see how it works. You might be able to do something like that, but this one isn't a tree really at all. You'll see how it works. OK, so anyway, the idea is we care about which digit is which and what it actually, which one they are decides which bucket it goes into. So here's how it works. We start with a bunch of numbers that are out of order. And I've made the numbers look weird. They are all 3-digit numbers. Okay? Even like 0, 1, 3. Even though it's a 2-digit number, I've written it 0, 1, 3 because doesn't 13 actually have a hundreds place? I mean, it does. It's just 0. And it has 1,000, and that's also 0. But we're doing it so that they're all the same length, because you do need to go through this for the maximum digits in whatever numbers you have. OK? And in this case, notice they're also all 0, 1s, 2s, or 3s. These are all base 4 numbers, technically. That's because it fits on the screen. Right? We only need 4 buckets instead of 10. But here's how it works. The first pass, you look at the ones digit, the least significant digit. You look at that one first. And it actually matters, as it turns out. You look at the units digit or the ones digit. And if there's a 0 in the ones digit, it goes in bucket 0. So notice 310, 130, 330, 120 all end with 0. I also purposely picked this data so it always fits in this little box here. It could be that they all end in 0. And then the 0 bucket would have all of them. And the other buckets would have none. OK? But in this case, they all fit there. OK, so you just do that. You put them all in the correct bucket. All the 0 ones that end in 0 go in that bucket. And then, once you've done that, you read them back into the original array. OK, you read them back into the original array such that you read this one, this one, this one, this one. You read them from 0 down to 3. So you read them left to right and then down. So 310 and 301, et cetera. And you put them back into the array, like that. OK? Notice all the 0 ones that ends in 0 here, and then the 1s are here, and so forth. OK? And you do the same thing again, except now you do it with the tens digit. Notice all the ones with a 0 in the middle digit are in the 0 bucket. And all the ones with a 1 in the middle digit are the 1 bucket. And you pull them out again. The act of pulling them out, if you do it in that order where you go left to right here and then down, you end up not disrupting the other order relative to each other. Okay, kind of like shell sort, doesn't disrupt the order in that case. Okay. Right, and then you do it again for the hundreds digit, and guess what? You do the hundreds digit. Okay, it means that anything with a 0 here is going to be in the 0 bucket, and then one bucket with the ones. And guess what you've just done? 0, 2, 13, 23, 32, 102, 111. They're now in order. Okay, which is pretty cool. And you never had to compare any of them together. Yeah?
Does this not work if you go backwards, the other way around?
We'll talk about that in a minute. If you go the other way around, the ordering doesn't end up the way you'd think it does. It ends up in a slightly different way, but we'll talk about that in a second. So hold on to that question. Yeah, went on and then. Yeah.
How do we find out how many buckets we need?
Oh, that's a great question. What would change the number of buckets? Well, how do you know how many buckets?
As in, like, how many times we need to
Yeah, that's it. That's what I thought you meant. How many times do you need to go through this? Well, you tell me. In this case, how many times do we absolutely have to go through this? 3 times. Why?
because they're the biggest numbers in the hundreds.
Because the biggest number is in the hundreds, right? But what if I threw in a 120 million in here? How many times do we have to go through it? 120. How many times did you have to go through it? 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to go through it 9 times, which isn't that many, really. But you would have to go through it 9 times, and there'd be lots of zeros. Would you need any more buckets? No, right? You wouldn't need any more buckets. You just need to go through it more times. OK, so how do you figure out how many times you need to go through it? So you find the maximum. Do you do that straight off and then say, now I know how many times I'm going to go through it? What do you do instead? You can do that. That's one way to do it. It just makes you go through the list one more time. What do you think you can do instead? Yeah, go ahead. Yeah, you find it the first time. You just keep track of the max the first time, and then you say, OK, now I know how many times. Do you have to go through it at least once? Doesn't every number have a ones place? Like if it's I mean, every number has a ones place, so you at least have to go through it once. But then once you get done with that first iteration, you can say, oh, now the max is 120 million. I need to go through it 9 times. You're looking at me like I'm crazy.
Just how would you do that through code? Because the first time we put it all in,
Mm-hmm.
I sorted it by the ones digit, and say it was 120 million and 1.
Mm-hmm.
And that wouldn't be at the very end.
So you can't really do a for loop, can you? Because you have to know before the for loop starts. So you just do some other loop, like a while loop or something. And you can figure it out in the middle. Yeah?
Then isn't it comparing numbers?
Isn't it comparing numbers?
No.
I guess so.
No.
I guess it's comparing numbers, but just once through. You're not doing any extra like comparisons. Yeah. Yeah. Nathan has his hand up first. Yeah.
So it gets out of comparing numbers to each other by comparing numbers to constants.
It gets out of comparing numbers to each other by comparing numbers to constants. That's a very good way of putting it. Yeah. Yeah.
Couldn't you also just keep going until all the numbers go into the 0 bucket? Just keep going.
Keep going until all the numbers go in the 0 bucket. Yeah, that would work too. Sure. Yep. You'd have to do that one extra time. So yeah. There we go. No more comparisons necessary. You could do it that way, sure. Yeah.
That wouldn't actually work. If you
Why?
had, like 2, 5.
Oh, you're right. If it happened to be, that's a good point. It wouldn't work. Sorry. You see why? What if you had all of them being 102, 205, 20, whatever? It doesn't work. You'd have to make sure that all the numbers weren't. You still have to do some comparisons. Yes, you would. All right, but you get the idea of this, right? You can do this. This is a radix sort. You don't actually have to compare the numbers to do the sorting themselves. Okay? Yeah.
Wait, hold on. What has happened? I'm not sure.
What just happened with the conversation here?
No, you were just like that.
Yeah, I didn't think about the idea that what if all the numbers happen to have a 0 as the second digit, but then they had other digits in there? Like we were thinking, like Alex brought up a good point. He said, hey, what if we just wait until they all end up in the 0 bucket, meaning we've gotten to the point where they're all less than, like they're all to the point where that digit isn't. Well, that's not necessarily the case. He tricked me. No. OK, good. All right, any other questions on radix sort? This is a fun one to code. By the way, normally we will use a queue for each bucket. So you can use a queue for each bucket. What queue are you going to use? You're going to go use the queues that you created for the other assignment. Just change it to ints instead of students. You've already got it built. The one for the ISIS course one. Yeah.
Just really quick, go through that example again.
Yeah. You go through the example again. So you start with unsorted. Then you do the least significant digit, the ones case. Put all the ones that are 0 in the ones digit in the 0 bucket, the ones in the 1 digit in the 1 bucket, the 2's in the ones digit in the 2 bucket, the 3's in the ones digit in the 3 bucket.
Okay.
Pull them all out in order from 0 to 3.
So, like, wait, can you go back? It would go 310, 130, 330, 120.
Yeah, and look,
112.
310, 130, 330, 120. Yep, exactly. Exactly. Good. Yeah.
And then,
OK. All right. So we're going to use queues to do this. You know what? I showed this Java applet in the other class, and it was stupid. And I had to reinstall Java on my computer, and they made security violations and all that baloney. You can look at this if you want to see it in action with the queues. Yeah. Really?
Can you look at integers like you do with strings and arrays and characters?
Ah, good question. Can you look at integers like you look at strings? You can turn an integer into a string, but that's going to be super slow. So you probably don't want to do that. That is a very good question, and we'll talk about that in a second, about the complexity. But yeah, you could if you turn it into a string, but you basically use modulus and divide to figure out what position the digit you're in. And that leads us to time complexity. The most interesting thing about this one is that the worst case is the number of digits in your longest number. If you have 120 million, you're going to have to do it 9 times, times n. Well, if 9 is a constant, and n is in here, and we pull the constant out, what does this become asymptotically? Order n, which is linear, which is actually better than all the other sorts we've talked about. Now, there's problems with that. To figure out which digit you're dealing with, to figure out that the 4 is in the tens place, well, you have to do a modulus operator, and that's expensive because it's a divide. And you have to do a divide, and that's expensive. Right? So there's the act of doing this adds a really big constant in here as well, because you have to do all that other calculation. Yeah.
Oh, yeah, I was going to keep it. I was going to ask if you treat numbers like an array.
You can't really, that's kind of the same thing. You can't really treat numbers as an array. Like there's no way to do that numerically. You can convert it into an array. Well, that's it. You could convert it to a string, but the act of doing that takes even more time. It's just not worth it. Winona?
Wouldn't this in general be bad for like small amounts of really big numbers?
Yeah, well, bad is a relative term. I mean, if you have remember, because we're dealing with only 10 buckets, there's not a limiting factor there. Okay? If we happen to have lots of small numbers in one giant one, OK, you have to go through it a bunch more times, and you end up making the same bucket over and over again. But it's not terrible. It is a specialized one. You're not going to use it for all different types of sorts. OK, you're not going to do that. Now, back to your question about if you do it in the opposite order, if you do the most significant bit first, right? If you do the most significant bit first, you end up with a different ordering. You end up with a lexicographic ordering, which is actually alphabetical. OK? You end up with an alphabetical ordering. Why? Take a look at this. B, D, E, bed, cat, bail, car. That becomes B, bail, bed, car, cat, D, and E if you do it this way. And isn't that the way we want it to be ordered for words? Right? B generally comes before bail. Bail definitely comes before bed. Think of it if this was a number, and these were numbers here. Wouldn't bed be a smaller number than bail? Because it's 3 digits instead of 4. And all 3-digit numbers are smaller than 4-digit numbers. So you would want to swap that in the case of doing it. If you did a least significant bit or least significant digit for this one, you would end up doing it in the wrong order that way. So if you're doing string data, doing it in the most significant bit works. If you did numbers using the most significant bit, look what happens. 1, 10, 2, 3, 4. That 10, why is it a 10? Because 1, it comes before 2, 3, 4, 5. You see? It's like you padded it the other side. Instead of the zeros like being on this side, it's like more zeros on the other side. See how that works? So you don't get the right one if you do it the most significant bit. Yeah?
So I'm just trying to understand, so like, in order to get like the 4 in the tens place from that number, what would you
Yeah.
would you going by would you modify something? Or just have to like what would actually
So you could do 542 divided by 10. That would give you 54, right? And then what could you do? You could do mod, you could do 54 mod 10. And then that would give you 4. And you'd go, OK. You know? So it would give you the 4. So that's how you'd get it. You have to do that calculation. Good. All right. Any other questions on this one? OK, I had a couple other things on a bucket sort. Think about what it would mean to go through a list once and have it sorted. Teachers kind of do this regularly when they sort papers. Not quite. They use a slightly different thing, but I'll let you think about that over the weekend. All right. See you guys next week.